All right, so these reactions involve the transfer of electrons. So we've been talking about electron structure. Now we're going to talk about how you can actually transfer electrons from one atom to another, sort of like what we've been talking about with ionic compounds. And there's two things that have to happen. One is something has to lose an electron, and then something else has to gain that electron. It always has to be, because it always needs to even out. So if you lose an electron, it's called oxidation. And if you gain an electron, it's called reduction. And that's why they're redox reactions, because you have to have both of them. You have to have the read, you have to have the ox all together, all right? Now, how do you remember which is which? Which one loses and which one gains electrons? That's what this is over here. Leo the lion says grr. All right, Leo the lion says grr, because Leo is loss of electrons, oxidation, and then grr is gained electrons, reduction, okay? So that part, not too complicated. Now we need to see this in an actual problem, like what would it look like if something lost an electron versus gained an electron? And we've actually seen this throughout the year already. All right, so let's talk about this right here. First of all, it was regular copper, and it was solid copper, plus what causes things to rust when you think about rusting or tarnishing? Oxygen, yeah, so let's combine it with some oxygen. And if you add water, if you add salt water, it speeds up the process, all right? All right, so what's the product gonna be? Well, we're gonna have Cu something and then O something, right? But we need to figure out charges and whatnot. What is oxygen's charge usually? Yeah, -2. All right, and copper's a transition metal, right? In this case, it happens to be +2. All right, so we're gonna have this. Now it's already balanced, right? So everything's cool with that. What would we call this? What would the name of it be? Copper what? Copper what oxide? Copper 2 oxide, right? Because of nomenclature, right? It's a transition metal, and you would have to say the charge in there, so it's copper 2 oxide. Good. All right, is the whole thing balanced? No, it's not. And this is going to be solid as well. Okay, so it's not balanced. What would you do to balance it? Where would you put some 2's? Yeah, in front of the copper, and then in front of the other copper, right? All right, that'll give us 2 of everything. And what kind of reaction is that? Yeah, synthesis. Good, a synthesis or combination reaction. Great. So look at all this that we're able to review in this chapter right before the 3rd marking period big test. Perfect. Okay, now we need to talk about what was oxidized, what was reduced in this problem. We haven't talked about this yet, but what's the charge of this copper right here? 0, right? It's 0, and it's also what we're going to call its oxidation number right now. It's just 0. It's neutral, 0. Let's keep it simple. We're just talking about charges, or refer to them as charges here. So this is 0. What about this oxygen here? What's the charge of this oxygen? It's right there. It's neutral, right? Because it's going to be 0, because what does that actually look like? If we drew it, it would be, you know, our oxygen, and then we'd have one bond there and another bond here. What kind of bond is that? Covalent, right? Double bond, covalent, polar, nonpolar? Nonpolar, right? Yeah, look at all the stuff we're reviewing. This is great. So we have this nonpolar bond here, so that's going to be a 0. Now, when does it become charged? When it's an ionic compound, right? So let's check this out. All right, let's look at the copper first. So we have copper, we have 2 coppers. They start out at 0, and then after the reaction, it becomes what charge? Plus what? +2. Okay, so did the copper lose or gain electrons by going through this process? Yeah, it lost some, right? It lost electrons. So if the copper lost electrons, what happened? Yeah, it was oxidized. So we would say that this one, because it's kind of like it's already happened to it, this one is oxidized, all right? So you'd have this right there. Any questions with that? How we figured that part out, all right? Now we need to write the electrons as well, all right? So because this lost electrons, what we would do is for the product side, we would put plus electrons, but you gotta tell me how many. How many electrons did it lose? And then there's how many of them? There's 2 of them, right? So what's the total number of electrons we lost?
4.
Yeah, we would lose 4 there, all right? So loss of 4 electrons, all right? Now this needs to be balanced out. So the oxygen should be the opposite. It should do the opposite. So let's look at oxygen. I'll do it down here. On the left side we have O2, and it's our neutral. And then over here, on the other side, we're gonna have 2 oxygens, and that one's gonna be -2, right? So what did it do? Did it gain or lose electrons? Yeah, in this case it gained electrons. So when you gain electrons, it's reduction, right? So we would say that this was reduced, all right? And how many electrons did it gain? 2 for each of them, but there's 4, or there's 2 and 2, so it's going to be 4, right? And then on this side, you would actually put it over here on the reactant side, because it's gaining and then it's becoming that one right there, all right? Now, if you look at this, here, the electrons are on the left side, and then over here, they're on the right side, right? So it's almost like they cancel out, because they're the same on both sides. It's kind of, if you think of it kind of like the spectator ions, it's kind of the same idea as far as like at least overall, the net problem is gonna lose the electrons because they're still staying in here. All right, does that make sense? All right, the other cool thing about this is if you were able to grab the electrons as this is losing the electrons before this gains the electrons, if you put something in between there, like, that's a bad light bulb, like a light bulb, that would actually light the light bulb up because that's electricity. So you have the electrons leaving here, going you through a wire, and then being kind of like captured by the oxygen. So the oxygen's gaining it. Does that make sense? Is that interesting? Yeah, look at that. That's how cell phone batteries work. Lithium ion batteries, there's actually lithium in there. All right, so they do the same thing here. You can actually make a light bulb light up if you just have metals in certain solutions because electricity can go through them. If you do some wire setup, we'll do that later on in the year.